Hi, everyone. Welcome. So, my name is Sebastian Garcia, and I'm going to talk about the network behavior of targeted attacks. In particular, we are going to model this traffic to identify it on the network. And this is part of a project that is called Stratosphere IPS project. That is the project I'm working with. Wait, I found the laser, this one here. So we are going to talk a little bit about how we are researching on detecting this malware in the network. So we are using some machine learning tools and trying to see what's working and what's not working. So here in the audience, who is working detecting malware or any type of botnet in the network? Who is working with there? There, upstairs, there, no one? No malware detection, no botnet? Okay. And specific some APT attacks, someone is focusing on APT, they say, hey, I just don't go there, we have someone there. Okay, so actually we are working with a lot of malware and botnets, but we like to focus on APT for two reasons. I will speak now about the first reason and later about the second one. The first reason for me is that APT, I'm not going to talk about, yeah, they are advanced. No, they are not advanced. They are persistent, not persistent. A lot of people know a lot about that. So what I like is that the goal of the APT is very specific, right? So when you are being attacked or they are attacking someone, they know who they want to attack, and they know what they want and how to get it. So this is not the usual malware that it's, I don't know, sending, click frauding on adware or spam or whatever, right? It's not money, or it's not usually a lot of money, but they are trying to get very specific information. And this is making the attacks very, very difficult to detect, right? In fact, they are not such advanced tools, right? What they are doing, it's like normal attacks. Some phishing emails, some malware, very simple RAT, remote access tool, and that's it. It's working, right? If you know the Citizen Lab people from Canada, they research on this a lot, and they found that most of the time they're using very, very normal malware, and only once they witness a zero-day attack in an APT case. So usually we are dealing with very simple stuff. The problem is that it's very difficult to analyze. So if you want to analyze, oh, there is people here. Oh, this is so close. So if you want to analyze APT, you can get the malware, you can analyze it, you can open the binary. It's not what I'm doing, right? I'm not a binary analysis guy. I like the network traffic. So how do you like the network traffic? Okay, I want network traffic. How do you get the network traffic? Okay, I can, I don't know, execute the malware, right? So I go there, I execute the malware. But what is the problem, or what is the difficulty of executing this APT malware in my network? Why it's not the same? What do you think? Well, you say, yeah, I have the real malware. I execute it. And even it's connecting, right? I will say that the malware is up, it's running, the command and control is running, it's there, everything is perfect. Why it's not the same, the analysis? No? Well, no human factor. In fact, it's something like that. I'm not the target. This is targeted attack. I am not the target. So they are not going to attack me as they are attacking some other guy, right? So it's very important being the target to have this traffic, because I don't care about the packets in there. I don't care if the packet is TCP or UDP. What I care is the intention of the attack. I want the behavior in here. I want the malware author saying, okay, now get the document files. No. Now forget the document files. Get the screenshots. Oh, hey, it's doing something. Get the keylogs. That's what I want. I want the intention here. I want the behavior. And that's why it's so difficult to get this information. So when we try to execute it, the first thing we found is the lifetime of the campaign is very short, right? So if you are executing the malware like 20 days after it's being captured in a real environment, that's it. You are not going to find the infrastructure there, the command and controls are not working, nobody's there listening, so the execution is not so good for us, right? So we can modify RAT malware. That's what we did. We get some normal malware, we modify it, and we execute it ourselves, and we attack ourselves, right? That is completely horrible. Specifically because there is no behavior. Yeah, I can attack myself. I can attack you. You can attack me. But we are not the real players here. So we did this to get the best traffic we can. But if you're analyzing this type of malware, this is an issue, OK? So this is the first reason why we are going to work with targeted attacks, because we like them, because they are very specific, very difficult to detect, and they are quite simple. But if you want to detect this in the network, imagine that you are going to detect this in the network, OK? So, is Misha there? You don't have a talk right now? No. Oh, OK, sorry. I thought he was giving a talk right now. OK. You can go to your talk if it's time for your talk. OK. So if you're trying to detect this in the network, right, you have solutions in there. You have a lot of software. What you doing? Real in the network. I'm not talking about antivirus stuff, right? I'm talking in your network. So you are putting some firewall in there, some IDS, IPS, filtering. You start playing with indicators of compromise, right? You are registered in a lot of feeds, so you get all this information, a lot of domains, URLs, IP addresses. Your feed is coming all the way, and you are blocking, filtering a lot. And also, you have a lot of fingerprints. So you have snort, you have bro. OK, actually, bro, it's not with fingerprints. It's with a beautiful language. But you are using fingerprints. You are using payloads, right? You are capturing this, and you are stopping them. And if this is not working, what do we have? Well, the latest of the tools we have is behavior, right? Anomaly detection. So a lot of people is working on this. Anomaly detection is nice. It's like a fuzzword. If you say anomaly detection, it's awesome, right? Nobody knows what's going on, but hey, yeah, we have some behavior in here. So what's the issue with anomaly detection? It's working. OK, who here is using some anomaly detection software or product in the network? No? Here? No one there? Oh, there, we have one. It's true. They exist. Now, this is working. The problem with anomaly detection is that for anomaly, you need to know what is normal. So you need the normal first, and then you spot the anomaly. And how do you know what's normal? Because we are human beings. We are changing all the time, our traffic, our patterns, our ideas. So that's an issue. If you go to the network, what is normal is changing all the time. So you should adapt again, and then you detect some anomalies. And then when you have the anomaly, it turns out that an anomaly is not an attack. And this is something that usually the people working with anomaly detection tend to forget. An anomaly is an anomaly. It's not an attack. So who is going to say if this anomaly is an attack? OK, so you need people there watching it and reviewing and saying, OK, yeah, this is an anomaly. No, yes, this is an attack. It's another attack. So it gets very, very complicated. And at the end, you need people working on that. So there are some issues here, right? The issues we have is that, first, the lifetime of the indicators of compromise is unknown. So you're blocking some domain. You're blocking some IP. How long are you going to block it? 1 day, 1 hour, 1 month? OK, how long is that IP in the list of blockers IP? Nobody knows. Well, some people is analyzing this, but usually this is not information you got in there. If you see the analysis, some information is there for 3 months, and 3 months is a lot. That domain is down and not working in less than 3 days, right? So why blocking it for 3 months? So nobody knows how to do this correctly. And of course, who is verifying this? Who is verifying that the domains you got for blocking are really, really malicious? Well, some people, I hope, I don't know. But if you go to virustotal.com and you search for www.google.com and you say, hey, VirusTotal, give me some indicators of that, you will find like 5,000 people saying this is malicious. And you will find like 17,000 people saying this is normal. So actually, this is confusing, right? If you have an automatic tool working with this data, you will have a lot of domains that are false positives, and you are blocking them. So the errors and the verification is very important, and nobody's looking at this right now. Oh, sorry. So also, you have a huge amount of information. One malware can generate dozens of domains, I don't know, dozens of IPs, plus payloads, plus fingerprints. So you are blocking a lot, more every day. And actually, you don't know what you are blocking. You don't know what you are not blocking. That's part of the game. And also, this information is static, so it's not changing, it's not evolving, it's not adapting. That's an issue. And finally, for the attackers, it's very, very easy to adapt to these measures, right? The cost of adapting, it's not so much. Changing IP, I have a lot. Like domain, I can register thousands, right? So I don't care. Actually, the issue with attackers is this: they don't care. I remember once in Reddit reading an AMA of a real botnet malware author, and he said, yeah, I have, I don't know, something like 100,000 bots, and I can use them. And I'm sending spam, and some user was asking the malware author, hey, how are you sending the malware and checking that the malware, sorry, not the malware, the spam, sending the spam and checking that the spam it's being read, and which is your best way of sending the spam in such a way? And the guy say, I don't care. Hey, but if you send the incorrect image, the people will know and they will won't be able to open your email. And he say, I don't care. You pay for me, I send your 1 million spam. You don't pay, I don't send. You pay me, I send. I don't care if the email is open or not open or whatever. They're making a lot of money and they have a lot of resources. So this is an issue, and most of them, they don't care. They just get another domain, they adapt, another IP, that's it. They're blocking it, regenerate the malware. It's difficult, yeah, it's costly, maybe, but it's not impossible, right? So we have this issue here. And with anomaly detection, like I told you, most of the time it's very, very difficult to know if it's working, right? So what are we going to do here? What we are working in the university is in some behavior method, but instead of focusing on anomaly detection, we are focusing on the behavior of the malware traffic. So we go to the network and say, okay, this is malware. I know it's malware because I'm analyzing it, and I want to learn which is the behavioral pattern of the malware in the network. And that's what we are going to do now. So the Stratosphere IPS project is the core of the project in the university. I didn't say, but it's in the university in Czech Republic. So you can find it online. Everything is published. And these are the 4 pillars or main ideas of the project. The first one is free software. Why we want free software here? It's not because we love free software. We love free software, but it's not because of that. It's because we know the community is able, and we want the community to verify what we are doing. We need the people checking it, downloading, testing it, and we need everyone saying, hey, this is not working, this is bullshit. No, this is working. You have errors in here. We can make it better. We can collaborate. We can send you stuff. We cannot, or stop doing that, or something like that. So free software is one of our main pillars. The second one is NGOs and civil society organizations. So at some point, the Citizen Lab people say that in their survey that the NGOs, the non-governmental organizations, they are in a critical situation because they don't have the resources to buy very complex tools for protection, right? They cannot buy from very large companies. But anyway, they are being attacked as a very, very powerful government. So for example, they work with the Dalai Lama in Tibet. It was attacked by China. So China is a very, very powerful country, and they attacked the Dalai Lama with success, right? It was completely successful, the attack. And they didn't have the resources, they didn't have the money, the people, they cannot defend themselves. So we are focusing in this type of organizations where they are very, very amazing targets for the attackers, but they don't know how to do it. They don't know how to defend. So this is the second pillar of the Stratosphere IPS project. The third one is the machine learning and the behavioral models. We want to have our research working in the network. We want to have, listen to this, our research to be useful. So we want actually to go to the network and plug it, and we want it to work. And this is usually the research people don't like this so much, right? You are doing something, it's awesome, you publish papers, a lot of them, and when you are trying it in a real environment, yeah, maybe it's not working. So, and the last pillar is the verification. We want this to be very, very verified. We want it to try as much as we can to see what's going on, how we are doing, it's having errors, it's not having errors, which errors, why we have these errors. So these are the 4 pillars of the Stratosphere. Now, how are we doing this? How are we working with machine learning in the traffic? So we start with this idea of less is more. So when we start working in machine learning, you can be tempted to work with a lot of features, and we are going to say that no, use less information. This is the first pillar that we are going to talk about. The second one is the disassociation. We are going to disassociate two models, and I'm going to show you now. And the third one is the verification, okay? So this means we are analyzing the behavior of the connections, not the behavior of the host and not the behavior of the network. This means that if you're going to the network, I don't care about the behavior of the 3,000 hosts. I care about one simple connection. And that's why we are able to create this behavioral model. Because if you try to create a behavioral model of a computer itself, it's very complex. The user is very complex. So we are not doing that. The second point is the disassociation. And that means that the representation of the behavior in the network, how we look at the behavior, it's separated from how we detect the behavior. Okay? Usually this is all together, but we are separating it. And finally, verify the models with real data. We need real data here. So, less is more. This means that when you connect to any other computer on internet, your behavior is the same. So you connect to Gmail and you are checking emails, you are chatting. The way you chat, the way you check Facebook, the way you use a website, the way you use your bank account is usually the same all the time. And this is going to identify your behavioral patterns, right? The second is that we group the flows, all the flows in the network go into a specific service all together. So imagine that you're connected to Gmail web server, so we get all the packets and flows that you are sending to that port 80 of Gmail, and we say, this is your connection, and we are going to analyze that. And finally, since the connection is composed of several flows, we can see the behavioral patterns in here. So, in the case of malware and in the case of you, when you are using, for example, any web page, you are going from one state to the other, like chatting, not chatting, like downloading stuff, no downloading stuff, like putting information in a web page, not putting, downloading a picture, looking at a picture, clicking in a picture. You are jumping from states to states, and that's what we want to model, right? So each flow it's going to get its own state in our model. I want to give you one state for each flow you have. And our model for the states, it's based on 4 features. And these are very simple, right? We are looking at the size of the flow, the duration of the flow, the periodicity of the flow, and the time between flows. So I'm not going to get into the periodicity because it's quite an issue to have that information, but you can see that this is very simple, right? It's like, why are you using this? You can have very, very amazing features in here. And the reason is that we try those amazing features and they're not working. They are too complex, right? And when the model is too complex, and then you go and check it, and if the model is not working, you don't know why. Or worse, when the model is working and you're detecting, you don't know why. So at some point, it's very, very difficult to work with that. And that's why we have these 4 features in here, okay? So what we are doing with these features? We are creating this table, horrible table. The table is saying, okay, you got one flow, okay? And the flow has a small size. And then the duration of the flow is maybe medium. And the periodicity of the flow is weak periodicity. So I'm going to give you a capital V. Or if the periodicity is weak and your size is medium and your duration is long, I will give you a capital F. Or you have a weak non-periodicity or strong non-periodicity. So we assign letters and numbers to each flow in the network based on these features, okay? And finally, we are using some symbols in here, like the dot, comma, plus, star, and 0, and it indicates the amount of time between the flows, because having a periodicity of 5 minutes is not the same as having a periodicity of 3 days, right? Periodicity is periodicity, but it's completely different behavior. So we are trying to get this information here, right? And if the flow has a timeout of 1 hour, we are putting a 0, okay? Special symbol there. So let me show you how we can look at this. Can we use it? Oh, thank you very much. Okay, so for example, I'm not sure if you can look at this. I will see. Can you see that or not? It's very, here, upstairs, can you see that? No? Completely no? Maybe if, can we turn down the lights a little bit in here? Can we try that? No? Okay. I will walk through it, don't worry. It's horrible anyway, so don't worry. So each line here is a connection. It's one computer connecting to other computer, connecting to some specific port. So each letter here identifies one flow, right? So here you can see that, for example, there is a connection to DNS service, these red letters that I'm sure you cannot get from there. So this is err dot, error plus. And if you see the letters, there are no periodicity in here, because the periodicity was between the letter A and the letter I, right? So if you go to err, you are not periodic anymore. So if you look at this, you can say, hey, actually, this is not periodic, and this is a port 80, and this is a normal connection. This is a normal computer doing everyday tasks. If you look at this specific connection, you will see that there is a very strange port, 9131, and you can see some periodicity in here, h-mean periodicity. And this is a Tor connection. So the web service of Tor, when you are updating the Tor service, you get some periodicity in there, right? So here you can see a lot of letters. As you can imagine, most of the connection is just 1 or 2 flows, right? Because it's normal web page. You go to a web page, download something, download an image, that's it. You are not accessing every web page for hours. So let me show you another one. So I will show you, for example, this one. This is a malware that is called Flu, and we will use it later. And you can see here that it's also connecting to a lot of UDP and TCP connections. This is not periodic at all. And then here we have some periodicity, I, age. You can see a pattern here, right? So this pattern is very, sorry if you didn't listen to me. It's very characteristic of this command and control, right? And here there is another command and control. This is a very periodic connection, and it's keeping on going and going and going. So this is one malware that is called Flu, and this is a real execution. So another one. I want to show you, for example, okay, the muref botnet, right? A real execution of the muref botnet. So we executed this in our lab, and you can see here a lot of connections to port 80, and look at this, wow, this is a command and control. But this is not periodic, right? And this one, yes, this is periodic, and this is not. And this is not periodic at all, right? So muref have different command and control, and each command and control is having a different behavioral pattern. Actually, we can know that this is a type of command and control, and this is another type of command and control. And you can see here, yeah, it's completely sending. And now this one is periodic, and you can see also the pattern, right? You can see here also some timeouts. So this is how the letters looks like. Wait for it. I want to show you, for example, this one. Oh, come on. So, no. Here. Okay. So this one is more difficult to see. But you know what it is? It's the activity traffic. So it's the traffic from your computers. So this is how the computers here are behaving, right? And you can see some people getting to some web pages, UDP traffic, TCP traffic, and most of the people is just connecting to web page and that's it, right? You can see that there are no periodicities, no command and control channel, nothing that it's behaving like something that looks malicious, right? So this is a very easy way to look at a lot of traffic. Here is for verification, right? But the tool is looking it automatically. And you can see like, okay, there is no model here that looks like a command and control channel or some attack or something like that. Of course, we are not trying to detect like a specific attack, like go into a web page and exploit and that's it, right? For that, you have antivirus, you have a lot of tools. We want to see what's going on in the network. We want to see the behavior here, right? That's why if you only have a very short attack, we are not going to get it, right? And actually, we cannot. The tool is not for that. We want to see when you are being attacked, like in an APT, and your documents are being exfiltrated, for example. This we can capture. So, wait. I wanted to see also. OK, I will show you the last one. It's a Zeus botnet. OK, come on. Zeus botnet. So this Zeus botnet is a very, very large capture. It's like 25 days. And you can see a lot of traffic here. Look at this, right? A lot of traffic. But you see strange stuff, right? I will stop it just so you can see. So you will see strange stuff like 0, 0, zeros and some periodicity. But then this is not periodic. But then it's periodic. But then it's not again. Do you know what this type of traffic is? This is the Zeus botnet connecting to Google. So these are all Google IP addresses, and Zeus is using Google for a lot of stuff. But you can see, if you remember the normal traffic, that even when you access Google, your traffic does not look like this. So we can differentiate between a normal Google connection and some malware abusing Google, right? And here, these are the command and controls, right? You can see a very periodic string in here, the behavior. Even this one, look at this. It's periodic, but we have 9 zeros. That means 9 hours between two flows. So Zeus is sending a flow, waiting 9 hours, and sending another one. And we can capture like this, right? You can see here the pattern, and we can create a model from that. So going back to the presentation. So once we have these letters, what's going on with the behaviors in here? So this malware is generating the same behavioral patterns over and over again. When it's connecting with the command and control, it's the same behavior. Actually, we can see when the command and control is down, because the malware keeps connecting, but the behavior is different, right? So we can distinguish these situations. Also, changing the behavior is very costly for the attacker, because if you want to connect to all your bots at the same time and you want to give orders at the same time, you need some type of synchronization in there. And if you lose the synchronization, it's more difficult for you. You cannot use all of them at the same time. It's maybe more difficult to make a DOS attack, right? So at some point, you can change the periodicity. It's OK. We can still capture the change. But you want to connect. If you don't want a command and control, you cannot control your bots. So you need a command and control, any command and control, right? And that's what it's costly for the attacker. So this behavior does not expire easily, of course. The infections can go unnoticed for hours. So how much time are you willing to wait for a solution in your network? Usually we say, I want real-time detection, real-time. I want to see the red light there, right? Very, very quickly. But actually, the computers can be infected for hours or days, and nobody knows, and nobody cares, right? So, and you can tell the administrator, yeah, go there and clean that computer, and it's going to take hours. So there is enough time here to capture the behavior we need. This should not work in 1 minute, right? And finally, we collect both normal and malware behavior. We want them both. We need to know what's normal. We need to know how normal looks like. And then we can implement this. So how we can implement a detection for this type of traffic? Okay, so this is the first part. You remember that this association, the letters, is how you look at the models. We are not doing detection in here. So far, no fancy machine learning. So now that we want to implement this for detection, how are we going to do that? So the Stratosphere project now it's implementing 2 models and 2 more are under working. I will talk about the first one, that is the interpretation of the transition from one letter to the other letter as a Markov change, okay? So, how are we doing this? Okay, this is very, very easy stuff, actually. If you have the letters in here, A, Z plus, D plus, D plus, we are looking at the transition from each letter to the next one. And this transition, we model it as a Markov change. That means that we have a matrix in here that's saying, okay, so the probability to go from the letter A to the letter comma, it's 1 or 100%, and the probability from comma to A is 0.5, and like that for everything. So we learn these transition probabilities, we create a matrix, and the matrix can be look like this. This is the same, right? It's just a diagram. But it's like, okay, from going from A to comma, the probability is 1. From comma to Z, it's 0.5. From Z to plus. So we can model how the transitions were in the original malware, okay? And when we have these transitions, we create these Markov models of the known behavior. So we can look at Zeus for a long time, or Muref, or any botnet, and we can capture this model, this behavior. We create the Markov change, the matrix, everything we need, and we have the model ready, okay? Now that we have these models that I know what they are, this is a command and control that is down, this is a command and control that is working, this is another type of attack. Now we can get unknown traffic from an unknown network, and we can try to compare and say, okay, the question is, which is the probability that this traffic was generated with this model? That's why we are using the Markov change. So we say, okay, well, the probability is actually very, very low. Okay, and which is the probability of being detected by the second model? Okay, it's like that. And the third one, and then we choose and we say, okay, from all these models, including the normal ones, the probability that you were generated by command and control botnet, it's this one, so I will say that you are a command and control. Okay? This is how it's being detected at the end. It's not perfect, of course, but so far it's working. So, I want to show you some more stuff. So, the first thing I will show you is how to see the difference between 2 models. So, let me show you. What is this? No, go away. Okay, so I will show you the difference between malware that it's called Zeus. You don't see there, it doesn't matter. It's called Zeus, and a malware is called Vavo. Oh, I'm not sure the name exactly. So the second malware, Vavo, was created by some people that maybe is here in the audience, I don't know, the Crisis Lab people there. So thank you very much, it was awesome. You go and see his talk later because you will learn a lot. They created this amazing malware, and they are trying to see how other tools detect it, right? So this is amazing for us because it's like, okay, something that is very real and very difficult and very well done. So most of the people that it's trying to detect that in the computer, they are trying in the host. But we are going to see how, oh, I have this one here. So how we can see the traffic between Vavo and other malware like Zeus. So this detection that we are going to do, oh, sorry, I copied the wrong line. I'm going to show you what happened if we compare the model of Vavo with the model of Zeus. And this is a comparison that it's saying, okay, so the distance between the Vavo malware and the Zeus malware is actually very close to 1 here. These are the first 10 flows. And this means that they are quite similar. The behavior of Vavo is quite similar to one of the behavior of Zeus. But if we keep looking at this, not 10 flows, but give me 30 flows, and we can see the behaviors start to change, start to diverge. And if we want more flows, like 50 flows, it's more different, and if we want 100 flows, it's more different. So every time we are putting more flows, we can see that the behavior between Vavo and Zeus starts diverging. This means that the early behavior of Vavo and this Zeus is similar, but later on in the network, they grow apart. So we are trying to use this Zeus behavior that we know for a long time to detect the Vavo traffic in the network. So for doing that, I will show you something like that. So this is gonna, I hope you see something in there. So I'm gonna run some experiment in the tool. I didn't tell you, but this is the Stratosphere testing framework. It's one of the tools we are having in the project for experimentation. So I'm going to run an experiment. I'm going to say, OK, use the Zeus model and get all the traffic from Vavo and tell me how you are detecting it. Tell me when you are detecting what, right? So when you run this, I don't care about the description. When you run this, it's saying, OK, I'm going to separate the traffic every time slot, like 5 minutes or 10 minutes or 15 minutes. And in each of these time slots, I will tell you if the models are matching or not. I will tell you, OK, yeah, I detect something, or I didn't detect something. So I will go back here, or up, sorry. And you can see, this is going to be very quick, but you can see here that in the first time slot, they're saying, OK, starting the time slot here, and it's from 00 minutes to 5 minutes. You can see that there are some IP addresses in the traffic, and there are no ground truth labels. That means that when I was looking at the traffic, there is no indication that this is a malware behavior yet. It's just some packets in there. And also, we didn't predict nothing. So there are no detections, no known traffic in there. Nothing happened so far. In the second time slot, I'm sorry, I used the blue letters in here. That is horrible from a design point of view. I'm sorry. But you will have to believe me. Here, in this blurry stuff, it says botnet. So it means that the Vavo malware in here, it's using this IP, and we know it's Vavo, it's using the command and control, and we put the label botnet in there. For sure, this is a botnet or a malware. But we didn't detect it, so our model is not matching here. So in the first 2 time slots, there are no detections. That's why the type of error is false negative, because we miss it. We didn't capture. But in the next time slot, that means that 15 minutes later, we were able to detect the Vavo botnet with the Zeus command and control model. So we have a true detection in here. We have a true positive. This means that at this point, the model matched, and we were able to capture it. We were able to detect it. But if you keep looking, the next time slots, we didn't detect it. Because you remember that I showed you that the models were diverging. The models get different from time to time. So after some point, this is not similar anymore, but was enough for detection, okay? So this is one way that we can experiment with this. And at the end of the experiment, yeah, you have what's being detected and not. You have all the fancy measures, true positive red, precision. You can have them all. And then you can see, okay, is this model enough for detection or not, or we need more, right? So this was an example of using a Zeus model for detection of Vavo. There are other models. We try also with a model called, I don't remember now, it was called botnet, okay. Another botnet that I don't get now, that also was able to detect Vavo, and then we can use now the Vavo model for other stuff. Of course, if I'm using the Vavo model for detecting Vavo, it will detect it, right? But hey, that's cheating because I don't know Vavo in advance. I should find Vavo in the network, using whichever tool I have. That's why we are using the models already in the database for detecting the new unknown traffic. So I will continue with the presentation. Yeah. So we can see the distance between models. We can experiment. Say, okay, use all these models in this traffic. Tell me what you find, and especially tell me what and when you find it. And this detection is done by generalizing the models. So I won't speak about that here, but sorry, the Markov Chain models can be generalized in such a way that we are detecting similar traffic, not exactly the same traffic, right? So I want to say something here. Sorry, yeah, here. The verification. Usually the people is asking, okay, and is it working or not? It's like if you go to any antivirus company or any protection company and you say, hey, your product is working or not? How do you know? I don't know, maybe yes, maybe no. It depends on a lot of stuff. There is no easy answer here. If somebody is telling you, yeah, our product is working very, very amazingly, I will doubt a lot. Because if I change the network, if I change the attack, if I change the timing, if I change the normal people, maybe if I change country, your detection is going to have some issues, for sure, right? That's why nothing is working so well. So for us, it's very important, the verification. So yeah, our model is working when, with this data set, with these levels, with these people, with this traffic, and this way of verifying. Because do you remember I showed you the experiment using 5 minutes time slot? If you're using 10 minutes or you're using 1 hour, the results are completely different. If you're using 1 minute, it's completely different. So also it means, how do you consider a detection successful? For example, you have a malware in there, and you want to say, yeah, I can detect it. What can you detect? Can you detect the whole traffic? Can you detect each packet as malicious? I say, no, well, each packet, maybe not. Okay, can you detect each flow, each connection? Each IP address, what can you detect? So it depends how do you count the detections, and then you have the final statistics saying, yeah, we have a false positive rate or F measure of 99.9999%, right? So be very careful when the people is giving you this type of results, and you say, yeah, it's amazing, or no, it's not working. Maybe it is. So we already said it depends on the data set, the time frame, and the verification method. And that's why we are using and we are publishing a very large data set of malware traffic. You can find it in the page of stratosphere.ips.org. You can go there, and there is our data set. You can download it, a lot of labels in there. You can ask questions, ask for new data sets or whatever, because we need this to be verified, right? And having malware data set is very, very difficult. But having normal dataset is far more difficult. Botnet dataset, we have a lot. But normal ones, who can have the traffic there with the labels that it's saying, yes, this is normal. So we are doing this, but it's very slowly. We are going to any computer and checking, like, is this normal? Okay, show me the computer. Yeah, you're not infected, you're not doing something stupid, you're not attacking or whatever. So, okay, this is normal traffic. So we are verifying it host by host, and that's why it's so important for us, this traffic. Finally, we want to compare approaches, what other tools are doing with this data set, what are they detecting, what they are not detecting, and this is very, very important for predicting the performance. So I will stop here. I want to say that the network behavior for us are very, very important, and we think that this type of work using machine learning, artificial intelligence, especially on behavior, it's going to give us very good tools in the future. So that's it. That's the webpage of the project if you want to go. Sorry, the people upstairs, you're not going to make it. But stratosphere.ips.org, and that's it. So, any questions? Oh, sorry.
Okay, question. What about traffic type like streaming video or playing video games on the network?
Yeah, okay. So the question was, what about traffic like streaming or computer games? And this is a very nice question because this specific type of traffic can be very, very tricky, right? For example, we have issues with tunneling protocols, VPNs, NAT, when you have like 1,000 computers behind one NAT, or even with DNS. Just the simple model of DNS. Imagine this. You are in a computer using DNS traffic, right? Normally, because you are normal, I hope, people doing normal stuff. And then you are infected. And the traffic of the DNS is mixed. Your traffic and the malware traffic is mixing one connection. So you have two different behaviors generating similar packets, and they are very difficult to distinguish. So far, all the gaming we saw and the streaming, we can differentiate. For example, our worst enemy, I will say, is the online music, like online radios. These type of websites are generating a periodicity that it's very hard to distinguish from other malware. So we have to be very careful with this model. That's why we are training them. And to each model, we can put, it doesn't matter, some thresholds here, saying, okay, this model is very good, this model is not so good. So when we are using it, we know where to draw the line. Okay, don't detect with this model so much because it's matching a lot of false positive, for example, right? And then the other part of the question is that in the future, what we are going to do is that we are going to get all the behaviors of your computer, and we are going to take a decision based on all of them. So I don't care if you are doing something malicious. What I want to know is, are you also doing something normal? And are you doing something like command and control? Like, how is the behavior of all your computer at the same time? So that's better for differentiating these very weird protocols. Yeah. But they are tricky, it's true. Sorry, another thing related with this is that when malware starts mimicking the normal behavior of the people, that's why it's very difficult to detect it, right? Yeah. The what, sorry? Servers. No, not so far. I have to say that if you care about, okay, the question is good in this sense. I don't care, or the people don't care so much being attacked, because you have a lot of way of stopping that. But the issue is that you cannot detect when you were attacked successfully and you are sending information and you are communicating when the attack was successful. So that's why we want to detect. When the attack was successful and nobody's detecting. Not the antivirus, not the firewall, not the anomaly detection, and you don't know what's going on. So that's in the place that we want to say, okay, we can detect that, right? The rest of the attack, we leave it to the firewall or the administrator. Yes. Another question there? Cannot see. No? The people that couldn't read the slides? No? There? No question? Okay, thank you very much and enjoy the rest of the conference. See ya.